Hello! I wanted to make a video answering a question that I saw on the Arduino for Beginners Facebook page. This is a Facebook page where beginners can join, they can ask their questions, and people can kind of chime in and help them through problems that they're having on the Arduino. So let's read through this question and see if we can help. Hey everyone, working on my first Arduino project and I've hit a wall. Haven't we all? That is a very common occurrence, so I feel for you. Using an Arduino Nano Every, I'm attempting to make a basic boost controller for a car. The concept is simple, using a pot to increase or decrease the duty cycle on a solenoid to display the duty cycle on an LCD display. The issue I've run into is I need to use a 33 Hertz on pin 9 to drive the solenoid. Apparently the timers work different on the Every, and I haven't been able to figure out how to change the frequency from 980 to 33. Does anyone have any insight? Thank you. Okay, so yes, we can help. We can dive in on how to configure PWM and how to change it to your desired frequency. You are absolutely correct that the Every has completely different registers to the Nano or the Uno. They use completely different chips. Arduino themselves have done a terrific job on kind of mitigating that fact a little bit. Their core libraries work just fine, and they have a little feature that works behind the scenes that translates the registers from the Uno to the Every, but it's not perfect. If you're going to do something this specific, you kind of have to do it manually. So we're going to look at the data sheet for the 4809, and we're going to look at what the registers are called, and we're going to call them, and we're going to configure the PWM the way you want it to be configured. Okay, in the comment section I saw an article that I believe they're working from, which is for the Nano and the Uno. So let's just, as a starting point, look at that article. I've skipped all the stuff where they just kind of gave you a basic overview of the Uno and the pins and blah blah blah, and went straight to their explanations. So they first start by defining the base frequency. The base frequency of microcontroller in Arduino Uno is defined as 31250 Hz for pins 3, 9, 10, and 11, and 62500 Hz for pins 5 and 6. Okay, so where do they get these values from? Now we know that the clock's frequency is 16 megahertz. So how do they get these weird values? The explanation for that is going to fall out of the explanation for how PWM works. So let's go over to a piece of paper and let's look at how PWM works. So you have a timer and it starts at 0. Let's say hexadecimal 0. Here's the base frequency, and then it counts up and up and up and up and up, and each tick of this increment is controlled by the clock, 16 megahertz. So every tick of 16 megahertz, there's a tick up in this counter, okay? And then it reaches the top value. Now, the counter in the Nano or Uno is an 8-bit counter, so the top value is hexadecimal FF. And when it reaches the top, it resets, okay? The counter keeps ticking away, it increases the counter, and then it resets. Increases and resets. So this is what the timer's doing behind the scenes, okay? So how do they get PWM out of that, you say? Okay, sure, there's this timer, but that doesn't look like a square wave. So there's also a compare register. I'm just going to say CMP. And then this is where they actually create that differing duty cycle square wave. So let's just assign the compare register to halfway between these two values, which is hexadecimal 80. And the point on the waveform is going to look pretty much like this, halfway in between. Okay, so this is CMP. So when the counter reaches the compare value, it slams the output high, okay? And then time traverses, and then when the timer resets, the signal resets. And then time traverses while the counter is counting, it's going to reach the compare value, and then it's going to slam the output high. Time traverses, timer resets, time traverses, compare registers met, blah blah blah, and so on. Okay, so we have 50% duty cycle because we have 50% of our top value. Hope that makes sense. Now, how does that explain where those values come from? So this is the value 256, this hexadecimal value, and that explains every position that this counter can occupy. So if every position is controlled by 16 megahertz, then 256 positions means we divide this by 256. Okay, so let's go to the calculator and actually see that in action. So let's open up the calc. I'm going to full screen it here. Make sure we're in decimal mode. So we have 16 megahertz, and then we divide that by 256. And looky here, we have 62500, and that is the value that we have right here. So we can deduce that pins 5 and 6, they use an 8-bit counter, and that they operate on this principle here. It counts up, it resets. It counts up, it resets, because we have 256 positions. Now, where do they get this other value from for these other pins? It looks like it's half of the value of the other one. Well, there's a different timer on that chip with a different mode. So let's go to the piece of paper again and outline how that timer operates. We have the bottom value, and then it counts up and up and up and up and up to the top value, which is also an 8-bit counter, so we still have 256 up here. However, this is what's called a dual slope mode timer. So instead of resetting, we just continue to count down. We count up, we count down, we count up, we count down. So we can still use our compare register the same exact way to get our PWM. Let's say we're at 50% duty. We have our compare points. The output slams high, it waits, slams low, it waits, slams high, waits, slams low, etc. So we can get the same thing out of a counter that takes longer to reset. So this half of the wave is 256, and this half of the wave is 256. So that's 512. So if we kind of deduce that they're dividing by 512 for that other value, we can see if that's the case. So main clock frequency divided by 512, let's go. Let's go to the desktop. Let's go back to calculator. We can go to 16 megahertz divided by 512. And there you go. We have 31250, just like we have in the article. So that's how they're getting their base frequency. So we're going to do the same exact thing on the Every. However, the Every is a lot more powerful than that chip. It's actually a 16-bit counter. So it's going to go all the way to FFFF, which is way, 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 way bigger. And then in dual slope mode, you double that again. So we're going to have way more timer counts to then divide our clock by. And another thing to touch on is a prescaler. Timers have what's called a prescaler, which takes your 16 megahertz and then divides it down before the timer increments so you can have different frequencies. Obviously, a PWM at 31,000 hertz is going to be pretty fast. This article defined one at about 30 hertz. And I can kind of go through the calculation on how they came across how to get 30 hertz. So what they did is they took their 16 megahertz clock, they divided it by their prescaler, which they set to 1024, which is the highest you can get, and then they divided it by 512, which means they're using this dual slope mode on their timer. And what does that equal? That equals about, 30 hertz. Let's look at that on the desktop. Calculator, 16 megahertz divided by their prescaler divided by 512. And there you go, 30 hertz. Now it's not exactly 30 hertz. I'm actually in the programmer calculator, so there's no decimals. Let's do that one more time. 1024 divided by 512. So it's a little bit off. It's 30.51-ish. So, and that's kind of what they say in their article. They say the following code generates a frequency of 30.64 hertz. So, I don't know, a little bit off. I don't know how they came across that specific decimal, but it's the same exact idea. Okay, so this is what we're going to do on the Every, but with the registers that they have provided for us there. So over here I have a blank sketch. Here's the Arduino IDE. The only thing different here is I have gone to Preferences and checked on Use External Editor because I like using Sublime Text. It has just some UI things that I'm more comfortable with. But if I put something in here, then it will be reflected in the IDE exactly. Okay, so let's go to a website. Let's go to Online Docs Microchip and go to this basically a search engine or repository. We're going to look up the datasheet for the 4809. So I'm going to filter by datasheet and I'm going to put in 4809 and we're going to click on the datasheet. So here's where we're going to find the registers to alter, and we're going to alter them. So let's start from ground one. Let's think about our clock speed. What is the clock speed on the Nano Every? By default, the IDE configures it to 16 megahertz, just like the Nano, just like the Uno. It does have the capability of doing 20 megahertz internal, but I'm sure they wanted to make sure it's one-to-one, just because they're doing a lot of stuff behind the scenes to really make it behave one-to-one. So I'm sure they wanted it to be just as close as possible. So in my code, I'm just going to remind myself of this fact. I'm going to say 16 megahertz clock speed. Okay. And the clock has a prescaler assigned to it as well, or it can, but I don't personally know in particular with the IDE if they set that or not. So for safety's sake, we're going to set it in our sketch. Now, it might be something we can just delete, it might not be, but I just want to be positive that we're dealing with 16 megahertz to start with. So let's just look at the AVR CPU section and the register summary, because there's a special register in here called CCP. Now, what does that register do? The main clock is quite important. Most people would agree. So they even implemented a lock to it. CCP is that lock. So to unlock the control registers for the CPU, you have to give it a specific byte value to say, okay, CPU, I'm serious, I know what I'm doing, I really want to change these registers, so here's the special key for me to be allowed to do that. So here's the values for that. So it has two keys for two functions. One is for self-programming, which we don't care about, and then the other one is unlock protected I/O registers, which is what we want to do. So I'm going to take this hexadecimal value and we're going to put this in our code. The register is called CCP, and then we give it the key that it wants, and I'm just going to call this unlock CPU registers. Cool, and save. Now that we've unlocked the registers, let's set the prescaler just to 0. Turn the prescaler off. We don't need nothing. We want that 16 megahertz, baby. So let's go to clock control, register summary, and find out where the prescaler happens. This first control register is where the clock selection happens. So your internal high frequency, external high frequency, we don't touch that. The IDE already did that. We want to make sure that the prescaler here in control B is set to 0. Now, here is the register. It holds 8 bits, and each bit in this memory location is like a toggle switch. It does different functions for different bit values. So this rightmost bit, the bit number 0, is called PEN, and that's prescaler enable. We want to disable it. So we make sure that that bit is a 0, and then none of the other bits matter because the prescaler is turned off. Okay, so let's just say, what was that called? Clock control, MC control. I'm just going to copy paste. and make sure I name this correctly. So the first thing I put is this main tab over here to the left, CLK CTRL. So clock CTRL, and then dot, kind of the sub register, if you will, that M clock control B or whatever. And then I set this to 0. And that is no CPU prescaler. I'm going to make sure that my comments line up here. Okay, cool. So we've taken care of that. We know our baseline is 16 megahertz, just like the example, just like the Uno. Next, let's worry about our pins. You saw in our article here, they referenced these different base frequencies for these different pins. So the Nano and Uno are pretty limited in what PWM pins you can use. The Every, on the other hand, is way more flexible. There's still some limitations, but it's highly configurable. So let's figure out where that happens. So I think there's a chart we can look at. Multiplexing considerations. This should be it. Ah, yes. Okay, so there's a column over here. Let me make sure. Oh, yeah, okay. Sorry, I'm using a trackpad, so the scrolling is a bit wonky here. Okay, so here's a column called TCA0. These are all the functions related to the timer counter A, which is the one we want to use for PWM. Now here are some waveform outputs defined. So WO0, WO1, these are our outputs. So PWM channel 0, PWM channel 1, yada yada yada. So by default, this waveform output 0 is configured behind the scenes to port A pin 0, PA0. I don't particularly like it on this pin because it has some other functions that are important that you might already be using, namely the UART, the serial. So the transmission line for serial port 0, the one that the USB port uses, is assigned to this pin, so we don't want to touch it. So we want to assign a different port somewhere else in our code with a different register to use our pin output. Let's see what pins that waveform output 0 are applicable to. So let's scroll down here. Here's another location that we can assign it to. Waveform output 0 can be on PB0. What does PB0 do normally? Well, there's multiple serial lines on this chip, and the third serial port is assigned to this pin. Most people don't use 3 serial ports. I'm still going to kind of move on and see what other options we have. Waveform output 0 can be assigned to PC0, so port C, pin 0. It also has a transmission line, or transmit line for serial, but it also has an alternate pin assignment for the MOSI line. So this can be used in more important jobs. I'm also going to skip this. The one that really caught my eye was waveform output 0 can be configured to port D pin 0, which all it is an analog pin. We have many analog pins. This is just kind of does no other function. We're not overriding anything if we want it. So I'm going to choose PD0 as our pin output for our wave output 0. Our TCA has multiple PWM outputs. I'm choosing 0, and I'm choosing the pin PD0 as the output. Okay, so we've looked at this chart. We've kind of decided in our head what we're going to do, but how do we do it? If I scroll down here, let me zoom out again and move this over to the left slightly. Sorry, I just don't want my camera to be in the way. I don't know why it keeps doing that. Okay, sorry about that. Okay, so note number 3 is dealing with what we want. Alternate pin positions. For selecting alternate positions, refer to the port mux documentation. Perfect. So it explained to us where we mess with all this, which is great. So let me bring open the left-hand navigation pane once again. let's scroll down to where it says port mux and see what registers it has for us. Okay, so there are different functions within the chip that you can configure in different ways, and we're just going to gloss over most of them because we don't care about them. There's an event control handler, we're not using it. There's serial, there's TWI, but then here are the timers. TCA, route A. This is exactly what we want. We want to route the outputs from the TCA to the port that we want. Okay, so if we scroll down here, here are the values that we put in the register to assign the port we're using. Port A is default, port B is optional, C is optional, and D is what we want. That is value number hexadecimal 3. And we want to put it in this register here, which occupies the first 3-bit locations, which is great. So let's copy the name of this register, and we want to put it under port mux. So let's go down here. Okay, call this port mux dot the register we want to alter equals a hexadecimal value of 3, which was in that chart. And this is assign port D as TCA output. Oops, I cannot type today. Output, perfect. Okay, so now that we've kind of determined with that chart and with our little configuration here which port and which pin we want to use, let's just use pin mode to set that as an output. So pin mode, and this is going to be an output. So what pin do we put here? I'm not quite sure if I can just say PD0. So let's see in the IDE if it will compile. If not, we can just look at the pinout and see what pin this corresponds to, and we'll make it happen that way otherwise. It's compiling. Okay, so PD0 was not declared. So let's go to the internet. Let's say Arduino Nano Every pinout. Let's click on any old one and look at the picture. Alright, let me scroll in here, and PD0 is on pin A3, the analog pin 3. So we don't need these anymore. Let's go to our code and change this to A3, okay? And this was assign PD0 as output. Cool. So our pins are enabled as output, and the port we want the timer to output on has been configured. Okay. So what else do we need? So that part is all done. We don't need any more ports or pin configurations. We can actually just go look at the timer, which it's a 16-bit timer, so it's a little different from what we just kind of whiteboarded on the piece of paper. But let's look at what registers it has for us, just to kind of get an idea of how we're going to manipulate all this. Okay, so Control A is the first register, so let's take a peek. Here's where our prescaler happens. So in the example article, they set a prescaler of 1024. We might not need that because our counter counts a way bigger number, but we will need it nonetheless somewhere down the line. I just don't know what value to put in there right now. So we're just going to copy the register, keep it the same, and we'll figure out what value to put in there later on. Okay, so this is going to be TCA 0 and Control A. Okay, so TCA 0. This is a bit of a weird thing. I'm going to put dot single here because we're going to be operating this in single mode, not split mode. Split mode is a completely different mode that this chip offers, which we don't use, but we have to designate one of them here. So we're using single mode, and then dot the register we're altering, and just call it 0, because we're going to alter this later on when we know what value to put in there. So timer prescaler. Cool. Let's look on the next register and see what it has to offer. Control B. Okay, so here's where we select our waveform generation mode. So this is how we can tell it, I want a dual slope, I want the normal mode, I want this, I want that. So these bottom 3 bits look like their waveform generation mode, WG mode. So let's look at, I believe they have a table here. Okay, so here's normal. Normal mode just counts up and up and up and resets. Up and up and up and resets. That's the sawtooth. Frequency mode, I believe it's like for tone generation, like all it does is create frequencies. There's no pulse width happening, so we don't want that. Single slope PWM, that's also triangle, single slope. And then the next one is dual slope. There's 3 variants of dual slope, but I just want the most basic vanilla one. So this hexadecimal value number 5 is the most basic dual slope mode. Okay? The only thing the other modes do is changes how the overflow interrupt behaves, which we're not even using. So technically we can use either one of these. So I'm just using the top most basic one. It's the one that behaves in the way that I would intuitively expect it to. So let's see, what register are we putting this value of 5 into? It's called Control B. Control B. Okay, so I'm just gonna duplicate this line because it's pretty much the same. Make it Control B and put hexadecimal 5 for our waveform generation mode. So we have dual slope mode. Cool. Now there's some other bits in this register that we need to enable. Now here's the last puzzle piece for actually putting waveform output 0 onto pin PD0. You can see there's these compare register enables, compare 0 enable, compare 1 enable. These are your waveform output enables right here. So compare 0 enable is waveform output 0 enable. So it's in bit position 4. We want to kind of figure out on a calculator what hexadecimal value that gives us. So let's open that up. Let's go to programmer's mode and go to the bit entry option. So first we start with the value 5. So hexadecimal 5. That's our waveform generation option. Next we want to toggle the 4th bit. So starting from 0, 0, 1, 2, 3, 4. Toggle the 4th bit, and that gives us hexadecimal value 15. Okay, let's take that down. Let's change the 5 indeed into a 15. So this is dual slope mode plus waveform output 0 enabled. Sweet. So ports enabled, pins set to an output, waveform output is enabled. So all the background wiring and routing has been done. Next, all we really have to do is worry about the calculation, the prescaling. So we have our main clock, 16 megahertz, some prescaler that's undetermined, a target frequency that we know to be 33 hertz, and then the fact that we're in dual slope mode. So in an 8-bit counter, 256 times 2, so we're going to have FFFF times 2, whatever that value is. I think it's 65535 or something like that. But anyways, let's continue on getting registers into our code and punching the values we know and putting a pin in the values we don't know. So let's keep going down the line here. Control C controls some stuff we don't care about. It does other things. Same with Control D, Control E, Control F. Like some of these have to do with interrupts and things like that. Actually, Control D we can just double check. It should be in normal mode by default, but this is where you enable the split mode. Since we're using that dot single syntax, let's just, for safety's sake, make sure that this is indeed in normal mode, normal single mode. So we'll go, let's duplicate this line, we'll erase, Control D equals 0, and that is normal mode. Sweet. Awesome. Perfect. Okay, everything else register wise I don't really think we need to configure. So we have like event control, interrupt control, debug, blah blah blah. There's a temporary register. Here's where we actually get into the 16-bit registers that this timer can utilize. This one is a background one. It needs it to operate. It does its own thing. There's special cases where you might need to know it, but we don't use it. Okay, there's a counter register. This holds the value of the current position of that counter. So along that curve, let's say it's, at F012 or whatever, that value would be reflected in this register. We don't need this for this application, but that's where it lives. The period register. This is important. This is the thing that separates the every from the Uno. It is way, way, way more powerful because of this register. This will set an arbitrary top value. So let's go to the piece of paper here, because this is quite important. So this waveform will go from 0 to top, okay? 0 to top, boom. 0 to top, boom. 0 to top, boom. What this PER register does for period is you can set whatever position you want. So instead of all this, it will go all the way to period, boom, all the way to period, boom, all the way to period, boom. And this can be any value within this whole range. And this is how we're going to fine tune to 33 hertz exactly. Because remember that other example? They were constrained with 16 megahertz. They were constrained with the prescalers that they gave them, and they were constrained with either 256 or 512. That's all they had to work with. But we can turn this, I guess, 512 theoretically into like 500 if we want to. But instead of this range, it's going to be a range of FF, which is way, way, way bigger. So we're not going to have to use a prescaler that's this big because of the division factor that's already happening. Hope that made sense. But the period register is extremely, extremely powerful. So let's just put that in our code. Worry about what value it has to be later. So this one's called PER. Okay, so duplicate that line. PER equals, let's set it to the default top, just the maximum 16-bit value of FFFF. And this is setting period. I guess parentheses, fine tune 33 hertz. Cool. Now the only other register that we're going to use is that compare register. You've learned what a compare register does. It's the part that you alter to create the different duty cycles within your program. So I'm just going to set it to 50%. So let's say duplicate this. What is the register called? Compare register normal mode. It's called CMP number. We're using waveform output 0, so we're using compare 0. Let's say CMP 0. And we're going to set this to half, so 8000. All right. And this is 50% duty cycle. Okay, these are all the registers that we're going to need. The only thing we have not figured out is the specific value of our prescaler and the specific value of our period register. Okay, let's work through that. So to the paper, let's write down our known values. We have 16 megahertz. Boom. Let's divide by 2. Why? Why are we dividing by 2? Because we're using dual slope mode. Remember, we have half of the timer's value here, which is like defined as the max top that the counter can even hold, and then half of the counter is over here. So it's actually FFFF times 2. So that's why we're dividing by 2 here, okay? 16 megahertz divided by 2 because we're in dual slope mode. Let's go ahead and divide by our prescaler, which we do not know yet, and then divide by our target frequency, which is 33 hertz. And what does that even give us? Well, that gives us our per register. That gives us that 16-bit value. So we need to make sure that this prescaler is set that when this is all said and done, that this value fits inside 16 bits. So it has to fit in something like this. So if it's over this, we change the prescaler. If it's not, then we're good to go. So let's just start from the first prescaler option, test it out, trial and error, and see where it takes us. Okay, so let's go to a calculator. Let's full screen this. And basically we're going to be looking at this hex value in the top left corner and making sure that the result fits in 16 bits. Okay, so let's work in decimal. Let's clear this, go to 16 megahertz. Okay, divide by 2 because we're in dual slope mode. We divide by 33 hertz, okay? And then let's arbitrarily test a prescaler and see if it works. We're going to test prescale by 2. So divide by 2, enter, and let's look at this in hexadecimal. Uh-oh, so it doesn't fit into 16 bits. So you can see it's kind of added this bit way over here. That's way too big. It needs to fit within FFFF. This is too large. So let's try that again. Let's try a prescaler of 4, because that's the next available option. So 16 megahertz, 1, 2, 3, 1, 2, 3. Divided by 2, we're in dual slope mode. Divided by 33, that's our target frequency. Then divided by prescaler of 4. Enter. Let's see what that is in hexadecimal. Ta-da! So we've done it. So ECBE is our per register, our period register. And the thing that got us there is prescaler value of 4, which we've gotten the 2 values we wanted to calculate out of the way in this little trial and error exercise. So let's copy this and put it into the per register. So ECBE. And then where do we have our timer prescaler? Here it is, Control A. So let's figure out how to make a prescaler of 4. Okay. So we got Control A. Oh, no, yeah, here it is, Control A. So the first bit of this register is enabling the prescale register. So let's open up a calculator. Let's clear this out and enable bit 1. So far we have a value of 1. Let's continue. What else do we want to put in here? So these next 3 bits is going to be some value from this table. Let's find 4. So hexadecimal value 2 corresponds to a division factor of 4. So we put 2 in the space that these 3 bits occupy. So let's go to the calculator. Starting from this first bit, not the 0th bit, but the first bit, we count 1 and 2. And that bit plus the enable bit has given us the hexadecimal value of 5. So that's our prescaler of 4. We just put 5 in that register we already wrote in our code. So Control A equals hexadecimal value of 5, and that's it. The only other thing I need to kind of mention is that the compare register can never exceed your top value, which is set by your period register. So ECBE, if your compare register is there, your duty cycle is 100%. Okay? If it's at 0, it's at 0%. If you want 50% duty cycle, you divide your period register by 2. So let's do that real quick. So ECBE divided by 2, 765F. Let's put that in here. 765F. Cool. So let's compile this and hope that it works. I'm going to get my Arduino, which is over here. It's on like a little development board. Okay, I can kind of see from the corner of my eye that that has compiled correctly. I'm going to assume that's all good to go. So we're just going to hit Control U to upload that. Let it kind of churn along. It's uploading there. Cool, and it's done. Some of you that haven't used the Every before might see this little yellow warning. That happens on every single Every compilation that I've ever done, so just ignore it. It's not important. I'm going to cut the clip here. Let's go to an oscilloscope and look at the waveform and see if it is indeed exactly 33 hertz like we measured. Okay, so we are on the bench. I have my Arduino hooked up. So ground is hooked up to ground of the oscilloscope, which is hooked up to A3 of the Nano Every. And here's our signal. It gives us a square wave of 50% like we programmed in. And then the frequency counter here gives us our 33 hertz. So we are successful. We can do a bit of a manual measurement if we want to. Let's say we go to time. I'm going to zoom in a little bit. Let's scooch it over. Oops. Let's scooch it over here. We're going to move our cursors. All right, line the left edge up with that. Line the right edge up over here. Cool. And then down here, it gives us our delta of 33.1 hertz. So that's probably the errors down to the internal clock speed being a little bit different due to the input voltage varying, or maybe just the resolution of this scope. Maybe these little cursors kind of aren't on the right pixel or whatever. But yeah, that's it. 33 hertz, PWM, set it with the compare register. Have a lot of fun. Thank you guys.